We are back once again with Daily LeetCode Day 86. It is a momentous day, particularly because it is Day 86. So we are back once again. We have some legendary comments from the Luffy One Piece Admiral himself. I'm just that guy. Day 85. Such a monumental day brings tears to my eyes. You bring joy to my eyes, brother. Feels strong, man. Always feels good to get support from the gang, right? And Thomas mentioned, because I think yesterday I mentioned yesterday's video was called I am the LC Easy Slayer, which is actually true. We are the LC Easy Slayers, so I mean it's an absolute bloodbath, right? When we see in any LC Easy that we see, I mean it's a problem, right? That's going to be solved. Right, and we mentioned that Thomas, right, is struggling with, he's over here on actually hard problems, right, with dynamic programming, right? So what can you say, right? We got to play the cards that we are dealt, so that's kind of what we're doing. So we have another day in the bank here, right? Day 86, we have some problems to solve, right? And I think we might be a problem on LC Easies. So we might be, yeah, we're a problem. So I think we have more LC Easies to solve. And Pascal, I remember actually solving Pascal's triangle once before. Never done Pascal's triangle too. So yeah, we're just gonna go through these problems. And yeah, I'm not gonna lie, there's a bit of, just feels good. It feels good to do some recovery running, right? It's hard to explain on video, of course, but there's been a lot of work being done behind the scenes. So this kind of feels like these 30-minute LC Easy days kind of feel like an off day, even though we're not really off. So yeah, it feels good, man. So more easies to be done. I also don't want to start solving things too quickly. So we're trying to go at a pace that's respectful to the problem and to the goal and the grind, but not so fast as to be kind of, I guess, just solving it for the sake of solving it or just practicing in bad form. So even in some of the problems we looked at yesterday, you might see me and I'm just like, I have a runnable solution which I can click run on and just see if it works. But I think that's bad practice because I should know with a great deal of certainty, is my algorithm actually going to work before I run it? I think it shows a better understanding. So that's what we try to aim for, right? Other than that, system design is still going well. We're still reading through Don Martin's system design primer. It's just a long piece of content. So yeah, we're reading about availability, scalability, CAP, CAP theorem, consistency versus availability versus partition tolerance. To be honest, I'm just saying these words, but I don't really understand them yet. So we plan to make progress on this topic. So yeah, it's been really interesting to read about system design. Learn system design ASAP is one of our best performing videos ever. And I think it's interesting. It seems to be one of the hardest skills to acquire. So I'd like to acquire that maybe just by doing a little bit every day. So that is the case. Another thing I've been thinking, we might try and do these things earlier in the day. So I've been thinking about maybe starting some things in the morning, maybe splitting the day up before work, and then after work I can work on other things. But yeah, I've been really thinking about that. So there might be something to that. So I've been thinking about that as well. And I've also been saying we're going to change the setup, but I think we'll get around to that as well. But yes, don't forget to join the Hyperbolic Coding Chamber. This is an actually crazy chamber. We have legendary algorithms in here slaying the algorithm demons on the daily. We have I'm Just That Guy, Thomas Wong, the Copy Ninja, Maypen, right? We have all these people who are absolutely decimating LeetCode problems. The solutions that we submit from the Discord, the solutions that people submit from the Discord actually take up so much processing power on LeetCode servers that we actually have special accounts that we log into. And yeah, maybe it's because our algorithms are very inefficient. So you're going to want to join the Discord, figure out how not to write algorithms that take up so much time and space complexity. We're just going to jump into it. So we have 30 minutes, and yeah, we're just going to jump into it for now. But yeah, make sure to join the Hyperbolic Coding Chamber, and we have 30 minutes today, so let's do that. So given the root of a binary tree, okay, given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. Interesting. Root to leaf path of target sum is shown below. So we can see with example 1, we have a tree here, 5, 4, right? We're given a tree as input here. Our target sum is 22. They're asking, is there a root to leaf path which sums to 22? And it seems there is one. In that case, seems to be 5, 4, 11, 2. Now, I have a few questions, right? Can there be multiple of these paths? And it looks like the path also cannot exist, so we're returning a Boolean whether or not that's the case. Our target sum is 5 here, and the only options we have here, right, either a target sum or a root to leaf path where we equal 3 and 4, so it doesn't exist. We can see that here the sum is 3 and the sum is 4. And if the array is empty, right, and our target sum is 0, since the tree is empty, there are no root to leaf paths, even though the target sum is 0. So just to start, we can say, right, return false if root equals nil, right? So just to start there, we know that we should be good on that case. Now, I think we can, the approach I'm thinking about initially going with is going to be a breadth first search based approach first. Because if we imagine here, we could start at 5, right? The root, we go to 5, right? We view our neighbors, go to 4 and 8, 11, 2. And each time we add an element onto the queue, it'll be actually a tuple where one value, right, will be the node's value currently, and the second value will be the node's sum, the sum of the path so far, right? So we can imagine that for the root node, the value that's going to exist in the queue is going to be 5, 0, right? Because before we visit that path, the sum for this node is going to be 0. Right. And so all we have to do is just continually keep checking the neighbors with this BFS, and then we should find the first leaf. We should find the path that we're searching for with a target sum of 22. The other thing we have to make sure is that we're ending at a leaf node, so a node with no children. So I think we can do this. So let's try this. So the goal is a BFS with modified Q, and the goal time and space complexity would be linear time and space in the worst case. So let's see if the key bindings are finally working. They're finally working again. So how could we template this algorithm? Well, the go would be, like we said, the BFS with the modified Q. So the Q equals our root to start with a path sum of 0, right? And then we'll say while Q.length does not equal 0, right? Then we'd like to continue processing elements from the queue. Now when we process element from the queue, we're going to destructure it into cur and path sum, right? We'll say Q.shift. And we're actually going to have a little bit worse time complexity because typically you would use queue with or queue or a deck or sequential data structure with constant time insertion at the front and removal at the front, and the same thing with the end. We don't have that. But yeah, so now we'll have cur, right, and path sum. We're going to say, right, if we'll say return true if cur.val, which is the value stored at the node, right, plus the path sum so far equals target sum, right? Otherwise, what we just want to do is say, hey, if we'll just do q.push cur.left. Oh, no. We also want to make sure we're not checking everything. We also want to make sure that the node itself, cur, is a leaf node. And so we add another case here. Right? We're going to say if cur, right, dot left equals nil, and cur dot right equals nil, and cur.val plus path sum equals target sum, then we want to return true, right? Otherwise, we just want to push the neighbors on. So we'll say q.push cur.left if cur.left does not equal nil. And we'll do the same. And this is Ruby syntax, but it's basically just saying, hey, return this value if this is true. So if the current node we have has no children and the current value plus the path sum so far is equal to target sum, then we found the first root to leaf path, root to leaf, what do they call it? Root to leaf path, such that the values along the path add up to target sum, right? And if the nodes left or right children exist, then we want to, if this is not true, right, then we'll keep going. We want to add the node's children and then keep going. If we make it outside, or if we don't exit through this line on 22 here, then we can confirm that this path doesn't exist. And so let's see if this makes sense for our first example. Our first example, we have 5 in the queue with a path sum of 0 so far. So we'll pull it off the queue because the queue isn't empty. And then we're going to say, okay, well, does 5 have no left or right children? Well, it does have children. So clearly we can't return, so we're just going to push 4 and 8. When we push 4, now I'm realizing we messed up. When we push values onto the queue, we want to continue the tuple pattern. And that tuple pattern is based off, right, the new node that we're going to be visiting, right? And basically, cur.val plus path sum. And this is actually hard to read, so I'll make it slightly smaller. And it's still still hard to read. The lines are long, and it might just be more readable if we just wrote it like JavaScript. So let's just do that. We'll just say if and right? And then we actually need something to end the while loop. Okay, so now, right, we're at here with 5. Now we're going to push on 4, right, onto the queue, right, with its new path sum now being cur.val, which was 0, plus path sum. Cur.val, which is 5, and path sum, which was 0. So we're going to push 4 on with a path sum so far of 5, right? And then we're going to push 8 on with also a path sum of 5. Now we're going to check, okay, does 4 have no children? It does have children, so we're going to push its children on, right? We're going to say push 11 on with cur.val 4 plus path sum, which is 9, right? Then we're going to do the same thing for 8. We'll do the same thing for 8. Right, and we're going to end up pushing on 13 for the path sum so far of 13 and 4. Then we're going to visit 11, right, and it does have children, so now we're going to do 11 plus 9, right, and push on 7 and 2 with a path sum of 20, right? So 7 and 2 are both going to have a path sum of 20. We're finally going to pull off 2, and we should get that 2 has no left or right children. And it's cur.val plus path sum equals target sum. So let's see if this works. I used the wrong operator there. And I used another one here that was wrong. Path sum. This works in the first case. And let's try example test cases. So it works in these cases. So it does seem to work, and I guess the goal of this algorithm, I guess the time complexity would be linear time. But if linear time with the optimal data structure, because we have to visit the entire tree in the worst case, and linear space as well in the term of the queue that we use. So it looks like they do what we did here with the stack. So, I mean, they use the stack for the BFS, which is strange, but I think that's good enough. So that's path sum, Pascal's triangle. So given an integer, row index, return the row indexed, zero indexed row of the Pascal's triangle. In Pascal's triangle, each number is the sum of the two numbers directly above it as shown. So given an integer, row index, return the row indexed, zero index row of the Pascal's triangle. Pascal's triangle, each number is the sum of the two numbers directly above it as shown. So here we're given row index 3, 0, 1, 2, 3. And talking about this fourth row here, they'd like us to return 1, 3, 3, 1. Interesting. So I think what they're looking for basically is, given a row index, return that row of Pascal's triangle. So I think one way we could go about it is calculate Pascal's triangle, return row index. And then return the row index. So that is interesting. Did you optimize the algorithm to use only O row index space? This gives me the idea that we could calculate this sequentially. So could we write an algorithm to calculate the rows in Pascal's triangle? So we know that the base of Pascal's triangle starts with at least an array of arrays that looks like this, right? So this top part here, 1, 1, 1, 1, is the base of Pascal's triangle. How could we continue to calculate the values here? So one thing we could do, what if we said, okay, we're going to iterate up to row index, right? For example, row index 3, right? Which means we need to calculate 2 more rows, which means that we have 1 and 2 for free. We start at index 2, right? Or we start at index 2, right? And then we iterate through index 2. And then we'd add the first element, and then add the 2 elements together, and then add the last element. So that would give us add first element, then elements together, then last. So that would give us, right, 1, right, 2, and then 1, which is the third zero indexed row. Oh no, it's not. It's the second zero indexed row. So what if we did that again? Right, we'd put 1, then do 1, add these together, then 1. So I think we could just do that, right? I think we could just do that. So let's just say that it seems to work. All right, let's say we start at index 1 and calculate up to row index. So we could say just to start, right? If we start with our base, which is predefined here, and we'll just say return Pascal sub row index if row index is less than or equal to 1. And we're also assuming that row index input's always valid, so it's always a valid integer. So that would work just for the base, right, that we'd have. And then from here, right, we want to start at index 1, so we could say 1, right, going up to and including row index dot each row, right? We want to do some work in the case where we generate a row for Pascal's triangle, and then at the end we could just return Pascal row sub index. So it's actually hard to tell how this would scale, but now we're going to just go to index number 2. So we'll just say starting at 0, right, and then going up until going up until Pascal sub row dot length, right? Because 2 has 2 elements. We want to do we actually want to do all 3 iterations, right? Because if we do it excluding of the end, we only ever do the first 2, the last 2. Actually, yeah, let's just do it like this. So we'll say this is going to be our current row, right? And we'll just call it current row IDX. And then here we're going to call our cur row, or we're going to call it our next row, right? Because we're going to calculate it by going through our current row. So now we're iterating through our current row. And we're going to have our current column, IDX, right? And now we're going to want to do some work. So basically, before we start, we're always going to add a 1 to the front, right? And then at the end of it, we're also always going to add a 1 at the end. And then we can always do Pascal.push next row. But in between there, we want to do all the calculations, right? So we want to say, we're starting at index 0, so you want to add index 0 and the index in front of it. So we'll say next row dot push subcur. It might be easier to read if we just did cur row equals Pascal sub cur row IDX, and then we'll just say cur row sub cur call idx plus cur row sub cur call idx plus 1. And then here I'm realizing we're probably going to want to stop 1 before the end. Which I think should give us what we're looking for. I hate to make this smaller, but so let's just check really quick. If we get row index 3, we're going to go from 1 dot dot row index, right? And then we're going to do, right, for each row index, we're going to start at 1. Next row is right going to start with a 1 because it does. We're going to do 0, right, up until cur row idx, right, which is the current row is 2, has a length of 2 minus 1. So 0, or I mean 2, right, minus 1, so 0 going to 1. We're going to have a column index of 0. We're going to say cur row is equal to Pascal sub cur row idx, which is true. It's equal to an array that has 1. Or yeah, it's equal to an array that has just 2 elements in it, 1 and 1. And we're going to say next row dot push cur row sub call sub idx, which is 0, plus the next one, which is 1, which would give us 2. We end, then we're going to push 1. Then we're going to push the next row. And then we're going to do the same thing again. Right? Because now row index is equal to 3. So we started at 1. Now we're going to go to 2. Right? So now we're going to go to 2, which is this in this row right here. We're going to give it. Now we're going to calculate the next row based off this row here. We're going to give it a 1 to start. Then we're going to go from 0, right, up to the length of it, which is 3 minus 1, which is 2. Right, we're going to do cur row equals this row right here. Next row dot push 1 and 2, which should give us 3. Go to the next index 2 and 1, which should give us 3. And then we should add a 1 at the end. And then we do Pascal dot push next row. So we actually trying to figure out if we need to be exclusive or exclusive. I think we can be actually exclusive. So we calculate the row index that we're interested in by stopping at the one right before it. So I think this works. Oh, I forgot to remove these lines up here. It works in the first case. Let's try some different examples. Works in these cases. All right, looks like it seems to work. It's hard to tell what the time complexity of this is, though. It's hard to tell what the time complexity of this is, and I feel like there's a way this could be I feel like there's a math cheat code to this problem to solve it without calculating up to a point. But technically, we did optimize it to use only O of row index extra space because the Pascal triangle we build is only a row index length. What is the time here? 1, 2, 3, 4, 5. So it looks like each row has exactly one more element than the last. Two, 3, so this is 6, and then 10. I think this actually might be pretty bad. I think if you gave this a, all right, well, what's factorial, I think? 5 factorial is equal to 5. No, it's equal to 5 times 4 times 3, I think, or something like that. Is there an addition version of factorial? Because this would be 5 plus 4 plus 3 plus 2 plus 1. So I actually don't know how you would write that. But I think factorial is multiplication, so it actually wouldn't work very well. It's going to use row index space. So O of row index space, where each array has row index or maybe factorial is addition. Let me check. Actually, I think I just had a brain blast, and I think the runtime for this function might actually be the Gauss formula. Because I think if you were to do n times n, what is it? N times n plus 1 over 2. If we did n times n plus 1 over 2, then we'd actually get the number of operations we're performing. So for example, we wanted to go up to row index, which is 3. We end up doing, there's actually index 4. So we have to kind of add 1, but it would be 4 times 4 plus 1, which is 5. 4 times 5 is 20 divided by 2 is 10 operations, which is what we get. 4 plus 3 plus 2 plus 1. So I think the time complexity would actually be the Gauss formula, which is basically n times n, maybe. N times n with row index space. Oh, so I think we're right because they end up coming up with k squared, which is basically n times n. O of k. Looks like there's a faster version. Some complexity, an extra space. So the dynamic programming approach is just as fast as the other approach. I knew there was a math. This one's probably like O of k. Yeah, I figured there's always some math approach. I'm interested to see this dynamic programming approach. The previous approach, we ended up making the same recursive calls repeatedly. Generate the entire fifth row. We have to call getNum. The getNum function. For a row and a column, for a row and a column, you can get the number at that column by just running getNum, by just recursing up. So I see what they're saying, and then you could memoize it. So is that what they do? They do a recursive call, and making the same recursive calls repeatedly. That's a cool solution. I think I'm okay with the counting up version. Plus, I don't think the version. I mean, the version we wrote is okay because it seems to get the semi-optimal time k squared, even though you can get up to k. But I think I'd be satisfied with that. So that would wrap up day 86.